various applications of PCA, and the intuition that we're trying to build up is PCA basically is a way to get a lower dimensional representation for a much higher dimensional vector. So one possibility we saw this PCA value here for doing linear discriminant analysis. From 2 dimensions we went down to 1 dimension. We want to be able to do this for, say, nearest neighbor classification. So this can become very expensive if you are computing distances between data points when the dimensionality is very high. So you've got a very high dimensional data point, and again think of images. You have a 1,000,000 dimensional vector and you want to do nearest neighbor classification, so you'll have to find distances, which means that you have to compute a norm in a 1,000,000 dimension. 1,000,000 is okay nowadays, but still at the same time, let's make them color image, then we are talking about 3,000,000 dimensions. So but on the other hand, if the 2 images can be represented by the mean plus just 2 singular vectors, then somehow I should be able to compare just 2 singular vectors and end up getting the difference very quickly. The mean is not going to contribute to the difference, so forget that. Then I've got the 2 singular vectors, and somehow the principal component should give me the measure of how far things are. So that's basically the intuition. So let gamma 1 contain the first k principal components for k reasonably large. So take P1s are actually the principal components, gamma 1s are the factor loadings. So X is approximately gamma 1 times P1. So this gives a very good approximation. If XA and XB are any 2 points in RD, then if I look at the difference between the two, XA minus XB transpose XA minus XB, then I'm writing them as using this principal component representation, gamma PA minus gamma PB, gamma PA minus gamma PB. Now I'm saying that this is approximately equal to gamma 1 because this is essentially saying that the first k of them are good enough approximation. So from here to here I approximated. Instead of gamma PA, I have gamma 1 P1A, gamma 1 P1B, and so on. Then I expanded this, you get P1A minus P1B transpose gamma 1 transpose gamma 1, P1A minus P1B. And I claim that this is exactly equal to this. Why is that? Because these are the principal components, so they are orthonormal. So this just becomes an identity matrix, and you end up getting just the differences in the principal components is enough. And so if X is 1,000,000 dimensional, but P1 is 2 dimensional, you end up getting this to be much cheaper. So going back to my images of 3s over here, or rather this actually gives me a much better way of looking at it. This image, each of these images 10,000 dimensional. So if I want to make a difference between those 2 images, I have to compute a 10,000 dimensional norm. Instead, I will take, the mean doesn't matter for distances, so that goes away. I take 48 principal components. I take each image and project it onto these factors and get 48 dimensional vector. So now when I want to take a difference between any 2 images, I take the difference of a 48 dimensional vector rather than a 10,000 dimensional vector. And if I want to do nearest neighbor classification, I can do it on this 48 dimensional vector as opposed to the 10,000 dimensional vector. So that's another way of getting views of PCA, and basically that's coming from this idea that these 2 vectors are pretty well approximated by just the first few principal components as opposed to the whole thing. There's also another very interesting thing, which is sometimes actually doing the PCA turns out to be better than doing the distances in the full dimensional space. So if I look at images, so one would think that, hey, taking this 48 dimensional vector and finding distances there should be somehow worse than doing the 10,000 dimensional vector because I've lost information. But if it turns out that in that 10,000 dimensional space a lot of it is noisy, then trying to find that differences might actually be worse than doing the 48 dimensional, because in the 48 dimensional space you have effectively filtered out all the noise that was there. So the plot that has in this one, this is a photograph, figure taken from Barber, finding the optimal PCA dimension to use for classifying handwritten digits using nearest neighbors. So it's the same example like one of those threes. 400 training examples are used and the validation error was plotted on 200 further examples. This is the number of eigenvalues that were taken, or the number of singular values that were taken. So if you take too few singular values, then you get a pretty number of errors is pretty large. Your number of error keeps coming down. This is a bit noisy here, so it's kind of coming down, and then it starts to go up again. So based on the validation error, we see a dimension of 19 approximately is reasonable, but this part is believable, that as you're taking more and more singular values, you get better and better performance. But this is the part that is actually interesting, that if you take more singular vectors, your out of sample performance becomes worse, because what you're basically doing is trying to train too much within sample. You're trying to keep too much information of variations in that sample that you kept, which is not of relevance to what happens outside of sample. And in this particular case, it turns out that PCA is working like a denoiser. It's trying to get rid of noise. You're not training to noise anymore, and therefore out of sample performance tends to become better. That's another feature of PCA that we should keep in mind. Okay, so this is an interesting idea which we will see later on. We'll see a variation of this called PLSA later on. In document analysis literature, PCA, I shouldn't say it was rediscovered, but it was branded under the name of latent semantic analysis. It's basically PCA adapted to documents in particular. But there are some interesting tricks that they play before attacking. I mean, this is another example where if you do the PCA on the right thing, you get good information. If you do PCA on something which is not appropriate, there is no information there. So a lot of the story behind latent semantic analysis is actually constructing the right matrix. So let's say there are D words in our dictionary, and there are n documents in a corpus. This is the story that we are interested in. Let Pjk denote the number of occurrences of the kth word in the jth document. Now you have to play a bit of a, you have to figure out in practice, you have to take care of the fact, what does a word mean? Because I know that the word means a collection of letters, but that's not what I meant, because sometimes if you add different additions, now how should I give you an example of that one?
Present tense, past tense of the same word.
Yeah, many forms of the same word, present tense, past tense. Sometimes you add few things, and plural versus singular. So all of those things are not going to be different information. So all of them falls under this category of something called stemming. You need to find the stem of the word and keep that. So here pretend that when I say that there are D words, these are stems already. You have done some stemming. So after that, I've found that Pjk denotes the number of occurrences of the kth word in the jth document. The bag of words representation of a document J is simply this vector, Pj1, Pj2, Pjd. It just collects all the words together, and this is called a bag of words representation because I've lost information. And the information that I lost was the ordering. There is information in ordering of these words which I completely lost. So how do I fix, since you guys know a little bit about this, how would I fix ordering if I wanted to still go to bag of words and keep some ordering into account? Sorry? So what happened here was that I took a document, I stemmed it, but even after stemming, the words were put in a certain sequence. That document has meaning because the words were put in a particular sequence. If I give you this bag of words, I take all the words and put them into a bag, that bag doesn't have any meaning. But the document had some meaning. So there was information lost between going from the document to this bag of words. And the missing part, the part that I lost, was the order of words. So if I want to keep some piece of the order of words, what would I be doing? What can I do to keep some part of the order of words and still do bag of words? No, I'm looking for a rather dumb solution here. I'm not looking for something very fancy. So the trick that people play is to use bigrams and trigrams. So instead of calling a word to be just the word itself, take the word and the next word, call that a compound word, or the word, the next word, and the next word, and they call that a compound word again. So the 2 words will be called bigrams and 3 words will be called trigrams. That will extend the that will increase the number of words in our dictionary, but it will keep some ordering into account. Maybe, and this will pick up the thing that sometimes 2 words together have a meaning. Each word separately has no meaning. I mean, not meaning, by meaning I don't mean the meaning of the word, but in terms of classification or in terms of doing anything, it's when the 2 words come together, they are much more important for classifying than if each of them comes separately. So that's a simple way of adding some ordering information. Okay? So you can try to do various kinds of statistical analysis on this vector Pj, but one thing that people do is to renormalize these numbers slightly differently. It's common to normalize this number, and the way to normalize this is to define something called term frequency. So term frequency Ji is the number of times that word I appears in document J divided by the number of words in document J. So Pji was the number of times word I appeared in document J. This is unnormalized. You normalize it by the total number of words that come into that document. Why would I want to do term frequency rather than just looking at the number of words? Why is it better? Why do you think intuitively it's better for me to use term frequency? What's that?
Some words will be more, but comparatively.
No, but this is only by document. Remember, all I've done is I've taken the number of words in a document and divided by the sum of the words in that document. There is nothing about rarity here.
Actually, it shows the
What's that? Exactly. Different documents have different sizes. One is a 1,000 word document, another is a 10 word document. And now when you look at this vector, the sum of these vectors is going to be 1,000 for the document 1, and the sum of this vector is going to be 10 for document 2. So if you are trying to compare those 2 documents, it doesn't make sense to compare their word counts. They are just off by scales. Whereas here you have renormalized them, and therefore the length of the document doesn't matter anymore. It does matter somewhat, but at least it's a little bit more mitigated than before. The next piece, which is what was referred to before, is something called inverse document frequency, IDFI. So IDFI is now this IDFI refers to a particular word I. The inverse document frequency vector that corresponds to a particular word is defined as the log of n divided by the number of documents that contain the word I. Okay? Remember, n is the total number of documents in my corpus. So n over the number of documents that contain the word I, this ratio is going to be a number greater than 1, because the denominator is always smaller than n. So this ratio turns out to be a number greater than 1. Log of that is going to be a positive number. Later on, this is going to be important, that this is a positive number. Okay? It is possible to use different definitions of IDFI as long as rarely occurring words are given more weight than when they do occur. So the idea here is that if a word is very rare, it should have a large weight. It should be given a higher weight compared to words that appear commonly. Many words that appear commonly actually are thrown out. The, a, and whatever of those kinds are just completely thrown out. And these will end up getting, so now the TF IDF representation will be given by that. So XJI, this is document, this is word. So in document J, word I, you first find the TF, which is the term frequency of word I in document J. and inflate it by the inverse document frequency of word I. So if a particular word is very infrequent, this number is high, you take the term frequency and inflate it by a larger amount. Now the corpus of documents are then represented by x1, x2, x3, xn. This is how I'm representing my corpus, and now I can do PCA on this. So LSA now, latent semantic analysis, is simply a matter of applying PCA to the variance covariance matrix of X, if you want this matrix, or directly applying SVD to it. Either you can take the matrix X and apply it to the variance covariance matrix that you construct from it. Essentially what that is being said is that you first take this X, subtract from it the mean of all these vectors, and then do an SVD on the remaining thing. With the interpretation that the principal directions, eigenvectors now define topics. So every eigenvector now tells me, okay, let's just look at this for a moment. Which way did I define? It's X transpose X. So what is the dimension of each of these vectors? Each of these vectors, the dimension is the number of words in my vocabulary, right? So when I do the PCA on this, I will get directions in terms of words. The directions will be in the dimension of words. And so each direction will tell me what is the combination of words that are relevant. It gives me weights in terms of words of various kinds, and that defines a topic. And the one weakness of LSA is that the eigenvectors can have negative components. How can a word contribute negatively to a topic? It doesn't make sense to do negative contribution to a topic. We will see later on, there is a new idea that's there furthermore in this document. Later on we'll talk about something called probabilistically latent semantic analysis, which overcomes this problem, and that's based on non-negative matrix factorization. Right now we are just simply doing PCA. Topic modeling is a very hot topic in the machine learning community right now. It is an extremely hot topic. They don't do it so in fact LSA and PLSA have been shown to be not as powerful as something else which is called LDA, latent Dirichlet allocation, and LDA turns out to be a stronger methodology for this. And the reason why this is becoming very important is because you have tons and tons of documents now, and what you want to do really is to do, somebody gives you a topic and you want to pick up all the documents that are of relevance. And so what you want to be able to do is classify these documents in a way where it's non-supervised. If you tell me what documents belong to which particular topic, then I can do supervised classification. But this is not supervised. What we are trying to do is we are trying to build topics directly from the words themselves. Just by the organization of the words, we say that these documents belong to one topic, those documents belong to another topic. So retrieval becomes easy, because now what I want to do is when somebody asks me, give me a articles on a particular area. So first I do a mapping from the area to the topics, then I go from the topics directly to the documents and retrieve them. So this has become a very hot topic, and it's been around. It's showing up in many different places. When you do DNA array analysis, you can think of the DNA array as a topic, and then you can start thinking about trying to decompose them into various patterns of genes. So the topic in that case will be which patterns of gene fire together. So this idea of looking for patterns in non-negative data is a fairly hot topic, and it's going to be interesting as well. So here's a very simple example that we have taken from Barber's book. A dictionary contains just 10 words: influenza, flu, headache, nose, temperature, bed, cat, dog, rabbit, pet. The document corpus contains 2,000 documents. Some articles discuss ailments, some of these discuss influenza, some articles are about pets, some articles are background articles unrelated to ailments. Some of the ailments articles are informal, use the word flu, whereas others use the more formal influenza. Each document is therefore represented by a 10-dimensional vector, xji is equal to 1 if the ith word occurs in the jth document, and xji is equal to 0. So here's what ended up happening over here. The top is the documents. So there are 2000 documents. Document data for a dictionary containing 10 words and 2000 documents. Black indicates that a word was present in the document, and white indicates it was not. So up here, basically these are the 2000 documents, these are the 10 words. If a word appears, it's black. If it doesn't appear, it's white. And these are basically black and white vectors that are going on. All right. The first topic contains two subtopics. So what has happened now is, so now what they have done is over here, you did LSA to this document and you ended up getting 3 topics, 1, 2 and 3. Each document now tells you what is for each of the documents, the level of this grayness tells you how important that topic is for that particular document. The first topic contains 2 subtopics which differ only in the usage of the word influenza and flu. The projections of each of the data points onto the 3 principal components end up giving you there. So it turns out that for a particular document, for each of these documents, you know what is the weight on the first topic, the second topic and the third topic. The topics over here, so for example, these documents look like they have equal weight on 2 of these topics. These documents look like they're putting most of their weight on the first topic. This guy is completely smeared out. They're completely useless. This is this part. Some articles are background articles unrelated to ailments. So this completely went away. This one puts most of the weight on the second topic. So here's where they're talking about the first topic contains 2 subtopics. So these 2 might be subtopics. And this is a completely unrelated topic that has been found out. Now, this is a rigged example so that it turns out that what has been shown here is actually the projections. So these are actually the components there, principal components, but the topic itself could have negative components, so it's very difficult to interpret what the topics themselves were. Now I want to go in a slightly different direction and talk about kernel PCAs. So this, let's see whether I want to go there. Yeah, okay, that's good. So what I want to do now is take this idea and tell you that the same notion of kernels that we had developed before, we can attack even PCAs using that. So one direction in which you can go is the following. So I want to sort of understand the structure of this vector x. One way I did before to understand the structure of that vector x is to say that I took the vector of all the various x's that I have and tried to understand how random or non-random they are. But maybe if I'm able to lift this vector into a higher dimensional space, I can get some simplification. And why can I get that simplification? Because I think that there are some nonlinear relationship between the various components. I can add that nonlinear relationship in this higher dimensional space and now do some linear analysis in this higher dimensional space and hope to get better structure. We are going in the same direction as we had gone when we were doing support vector machines. So I define a feature vector phi x, which is in R capital D, where capital D is much larger than smaller d. Suppose x is equal to x tilde is the lifted values, x tilde 1 through x tilde n. Suppose for the moment the mean is equal to 0. We'll fix this later in just a slide. And define the covariance matrix to be x tilde transpose 1 over n minus 1. Let E be an eigenvector of this matrix with eigenvalue lambda not equal to 0. So if it has a 0 eigenvalue, I don't really care about it because that means that this matrix doesn't have any variance in that direction. But suppose its lambda is not equal to 0, then I can write this eigenvalue eigenvector decomposition. You get 1 over n minus 1. I will tell you why I'm doing this calculation in a moment. X tilde transpose E equals lambda E. If I multiply by x tilde transpose on the right hand side, I get x tilde transpose x tilde x tilde transpose E is equal to lambda x tilde transpose E. Let's define a new vector f which is x tilde transpose E, everything over here. So what have I done so far in going from all of this? I took the vector x, I lifted it to a higher dimensional space, constructed this matrix, and this matrix is huge. It has a very high dimension because it's x tilde, which has a high dimension. This says x tilde transpose, which is high there. So this matrix is a d by d matrix. Okay? So, and I'm looking for eigenvectors that are d by d. Now, what is x tilde transpose? That is n by d. So if I hit it over here, now I have a vector which is a little bit lower dimensional, that at least is in dimension n, which is the number of data points, as opposed to d, which would be very high. So I construct that. Then note that x tilde transpose x tilde ij is phi xi transpose phi xj. This is nothing but the Gram matrix. So if that is the feature vector, then this component is simply the Gram matrix kxi xj, which is written as kj. So this matrix, this relationship can be written as 1 over n minus 1 kf is equal to lambda f. Having computed f by solving for, we can recover E as follows: x tilde f is equal to x tilde transpose E, which is n minus 1 lambda E. And we can, corresponding kernel principal components are given by x tilde transpose E, which is x tilde transpose x tilde f. You put it all together, this is what happens. Now, what is going on over here? Let me unpack everything. I have this matrix, I have this vector x, I have a collection of vectors x1 through xn, and I want to do a PCA on them. So I could have done the PCA in just the lower dimensional space, but now I want to lift this guy into a higher dimensional space and do my PCA there. What does it mean to do a PCA? It means find the eigenvectors and then tell me what is the loading on each of these eigenvectors, because I want to represent this vector x by the loadings, which are called the principal components on these eigenvectors. Lot of algebra over here, but ultimately what happens is that I can construct now another eigenvector eigenvalue decomposition problem, which involves the Gram matrix of a kernel. This is no longer in a lower dimensional space, this is a kernel that is there. I can solve this, and if I want the principal component, I want x tilde transpose E. E is the eigenvector here. I want to project x tilde onto E, and you end up getting, basically you can recover this principal component by computing f and constructing this component. This idea over here, it's 1 over lambda n minus 1. Lambda is the eigenvalue right there, that sits over here. Kxxl is the kernel, fl are the values that you get from there. So once you solve this eigenvalue eigenvector decomposition, you can construct a principal component for the vector which is coming from the kernel. So the whole story here is that now, instead of looking at inner products in the lower dimensional space, I'm looking at inner product in a much higher dimensional space, and basically the same story will go through. Now what we want to do is, we had implicitly assumed that this thing is equal to 0. So what we do is we define centered feature vectors, which is phi hat, which is phi xi minus the mean. This gives me a new Gram matrix k hat. K hat is the Gram matrix which is phi x transpose phi xj. You plug this value in, you expand everything, and you end up getting that the new Gram matrix looks like that. So instead of solving this eigenvector eigenvalue decomposition problem using k, now you solve it using k hat, and you get what we want to do. So that is beautiful. You can get these principal components, you end up getting, you can squeeze out more information using this, but there are issues with kernel PCA. And the main issue is, in regular PCA we can use the principal directions, the eigenvectors corresponding to the largest eigenvalues, to construct good approximations. That is, if I have x is equal to gamma times p, then I can approximate it by gamma 1 times p1, which is a lower dimensional space. We can also do this in kernel PCA, but the approximation now lies in a much higher dimensional space RD, which is hard to visualize or interpret this approximation because it's now in the feature space. Would prefer to project it back into the original space, but this is generally hard to do because the mapping x to phi x is nonlinear. One possibility is to solve this optimization problem, phi x prime minus z transpose phi x prime minus z over x prime, where z is the approximation of phi x given by the kernel PCA. So you take the x, you construct an approximation, these are the principal components, and then you try to find an x prime which is close to that. Generally computationally intensive non-convex optimization problem. Okay, here's a picture. Schematic illustration of kernel PCA, a data set in the original data space. This is the left hand plot. Is projected by a nonlinear transformation phi x into the feature space on the right hand side plot. This is what happened. So this is intuitively what you should think about. Why we want to do kernel PCA. You look at this plot, it looks like, if you look at these data points, they are sitting on a curve. But if you did PCA on this, you will never discover it. Because PCA is going to find orthogonal directions here. It will either go that way and this way or that way. Regardless of which direction, two orthogonal directions that you pick, the projections on those two orthogonal directions is non-trivial. So if you did PCA on this directly, you will find that both eigenvalues are important. They are both going to be important. You won't be able to kill anything. If you chose the right kernel, which is able to pick this curvature, basically this is the level, you end up getting this as the direction. There is an orthogonal direction to this as well, but the orthogonal direction is so tight I can ignore it. By performing PCA in the feature space, we obtain principal components, of which the first is shown in blue and is denoted by V1. The green lines in the feature space indicate the linear projections onto the first principal component, which correspond to nonlinear projections in the original data space. Know that in general it is not possible to represent nonlinear principal components by a vector in the X space. So going back from here to there is very difficult, but it can be done. Now why would I bother with this even though going from there to here is difficult? Why would I care about kernel PCA even though it has all of these problems? What might be so let's look at this picture. Why might I care about still doing kernel PCA even though I know that from getting this picture to that picture is difficult? Sorry? Linearity, yes, but what, so linearity is useful, but in some ways the fact that this is linear, I can't get anything out of it because I can't do any projections back here. So why would I still want to do something like this?
Proportionality will be maintained?
Not necessarily. So the way to think about it is the following. Let's say that this is one class of data points. There's perhaps another class of data point which has some other curvilinear structure there, and I want to do a classification on those data points. I don't really care about representing these data points very well. I don't care about what the structure is. What I want to do is I want to classify them well. One possibility to do it is first do this nonlinear transformation and then do the classification over here in the transformed space. There it is the case that I can't go back and reconstruct for you the points here, but I don't really care. I only care about processing those points so that I end up getting a good final answer. So if this typically happens to be an intermediate part in doing something else later. So the PCA part is being done so that I get a better representation of the data points that I can use later for doing processing. It's not that I'm trying to find better structure in the data anymore. I'm just trying to summarize information that lets me do processing later on. This is why this kernel PCA is still important even though I don't get a good representation. So this time around, for example over here, in this case, I was after these topics. That's what had meaning to me. Or in the image case, wherever it was for back there somewhere, I was interested in knowing what these eigenvectors look like. But in kernel PCAs, those things are going to be unimportant. The only thing that I'll care about is, can I do good classification based on the principal components? And that's the end of the story. Question?
So, say this is your training set history data you have, and you have this kind of curve, PCA, and you do a kernel PCA to get that lead. Probably in the validation set, you might have slightly more tilted curve.
Sure.
That won't be projected in the same way that this is.
Yes.
Then how is our answer going to correct that?
So the way to think about it is that, look, if your test and that, so if what is important is just this cover, so the way to think about this is that this curve got moved to that quantity. Kernels tend to be continuous. The kernel function, remember, RBFs, polynomial, they're all continuous functions. So if this guy gets tilted a little bit up, a little bit down, then when their projection is going to happen over here, this won't be exactly a straight line, but maybe a slightly tilted straight line. If the difference between the training set and the test set is huge, then you're hopeless. On the other hand, if they are close by, but slightly more tilted compared to the other one, we will see that it won't come to be exactly the straight line, but they'll have a little bit of a trend somewhere. So in this particular case, the way this thing has been drawn, the data points orthogonal to this blue line have no trend. They are positive, negatively distributed. But in the test set, it's possible that you will get a trend, that maybe it starts from there and goes down there. You can still be able to do some structural story there. But again, all of this is essentially trying to say that I give you a little bit more freedom. I give you another freedom of using some nonlinear transformation to straighten things out and then do PCA, effectively do PCA in this sort of nonlinear space. Will it always work? No. It's just another tool in your toolkit.
So how do we decide when to use the kernels?
Cross-validation. So remember, if I set my kernel to be X transpose Y, I get back my PCA. So what you do is you do exactly the same thing. Suppose you're talking about classification, or you're talking about feature. You want to use PCA as an ingredient to do something else. You could use your old kernel, which is just X transpose Y kernel, to do your PCA. You do out of sample performance of that and see how it performs. Then you use some other kernel, see out of sample how it performs. And then, what's that?
Trial error method.
Not trial. Yes, you try different kernels, but not a trial and error, but you do, the training, test, validation, and from that you can choose what is the best kernel that is working for your application. This one just gives you before you knew kernel PCA, the only idea that you had was to do PCA. Now you have the idea of adding a kernel and you have a little bit more freedom to do things.
So what we wanted was, I need to have some intuition like, okay, my data is this way, I need to go for kernel PCA rather than spending more time on checking 10 different kernels and getting our answers.
Now with computation, it doesn't really matter, right? You just let it run. In some ways, in high dimensional spaces, intuition is completely dead.
There are these T and plots.
Yes, sir.
Are they doing the same job?
Somewhat similar jobs. Somewhat similar.
Maps and the TSN.
Yeah, they are trying to get to this nonlinear sort of relationships. This one is a little bit more mathematically justifiable. The other one's a little bit more heuristic. That's all. All right. This is another. Here, what's going on is this example is for kernel PCA with a Gaussian kernel applied to a synthetic data set in 2 dimensions. The first 8 eigenfunctions are shown with their eigenvalues. So this is now just sort of for the. It's trying to pick out where the eigenvector. So these are the 3 classes. We are trying to, the data is structured in such a way there are 3 different points, and now what we are trying to do is use an RBF kernel based eigenfunctions to see what is the relationship between them. The contour lines are lines along which the projection onto the corresponding principal component is constant. That's what the various contour lines are. Note how the first two eigenvectors separate the three clusters. So the first two eigenvectors, all of these points are sitting in one value for the eigenvector. All of these points are sitting in another value. These are somewhere else. Here these are clustered together, whereas these are sitting in sort of they fall into the same bin. These guys are separate here. These two fall into the same bin. That guy is separate. The next three eigenvectors split the clusters into halves. So they are dividing them by half. And the following three eigenvectors, again, they split the clusters into half along directions orthogonal to the previous splits. So if you compare this guy with that guy, so that guy is splitting in this direction, this guy is splitting in that direction. And if you compare this one with that one, this one is splitting there and that one is splitting that. Compare this one with that one, you've got a split in this direction and you've got a split in that direction. So they're trying to find these splits, and the way to think about this is if this data, if I were to just not have the kernel PCA under my control, there is no way I can find structures there, because no matter which orthogonal direction I pick, there is projections, there are good projections in that direction. So what they're trying to do through this RBF kernel is localizing these points. And it's one thing to keep in mind, of course, is both this picture and this picture is contrived. It's contrived to actually show you what these kernel PCAs are doing. In reality, things are not going to turn out to be as beautiful as this, but hopefully you can still be able to extract some structure out of them. Okay, a different story now. Okay, here what we are going to do is talk about a sparse PCA. So recall the PCA of a matrix X is U D V transpose, where V is the principal components, U are the factor loadings. We want the UIs to be sparse. Why do we want the UIs to be sparse? Because they are easier to interpret the principal components. So the principal component turns out to be UI transpose X. This is, say, the ith principal component. I don't know, what do we want to call this? BI. That's the donation that I had used. Typically, this, if you just do PCA, this eigenvectors turn out to be completely dense. If you're lucky, maybe they will turn out to be sparse, but in general they are dense, which means that this principal component depends on every component of the X vector. But we don't want that. What we want is to be able to say that somehow it picks out few components of the X vector, and that's how things are going to be represented. Now, in order to do that, here's the problem that people have set up. The first piece simply says X is equal to UV transpose. There is an error here. This should be V and not U, not A. So minimize V and U. So the first one just says X minus UV transpose, Frobenius norm. And there's also a major error here. This lambda belongs there actually. I'll fix this. So it's X minus UV transpose Frobenius norm squared plus lambda times the sum of I going from 1 through K of UI, the zeroth norm. So what is going on here is that the zeroth norm of a vector is just the summation of all the components that are greater than 0. It counts a number of non-zero terms in U. So this one says that I want to, when I put the lambda on this side, this one is trying to minimize the error between X equals UV transpose, whereas this one's saying that don't use too many components in any vector U. This is a hard optimization problem, and so what people do is you replace it by the L0 norm by the L1 norm. An L1 norm of a vector is defined as the sum of the absolute values. This has been used as a heuristic for a very long time, and recently solutions computing using L1 norm have been shown are the same as those computed using the L0 norm with high probability. The L1 norm now results in a lasso-like formulation. X minus UV transpose Frobenius norm squared plus lambda times the L1 norm of all of that. You're trying to find u and v which solves this. This is a non-convex problem and it's solved using coordinate descent. And tomorrow I'll show you some a package that is able to solve this and show you some numerical results for what happens here. Here's another story of something similar, which is called dictionary learning. Here now again you have the d by n matrix. We want to construct, and then once I tell you what's going on over here, we'll go back to the previous one and try to see exactly what is the difference between dictionary learning and sparse PCA. So here what's going to happen is that you've got a dictionary D of size d by r, a collection of representation vectors w1 through wn. For each of these x's I have w1 through wn. I want the xi's to be approximately d times wi, and I want wi's to be sparse. Then the L1 optimization problem would be 1/2 plus xi minus dw squared plus lambda times the L1 norm of the w's. Again, this is a non-convex problem which is solved using coordinate descent, once in d, once in w. So look at this formulation and look at that formulation. So what is the difference between these two? Here you're finding u v transpose, you want some of them to be sparse. U has u1 through uk, v has v1 through vk, which is in rdk, and you want to be able to find this approximation to happen. Whereas over here you have a dictionary and you're finding representation vectors that does the same thing. One is called dictionary learning, the other one is called sparse PCA. Are they two names for the same thing, or are these potentially something different? So ideas? Okay, so the difference between the two is that in one case you are really trying to find this u and v which are orthogonal. We really are trying to do PCA like things, and in PCA you want u and v to be orthogonal. In this case I don't really care. The dictionary D could be huge. There's no need for orthogonality. And there what people are saying is that interpretation is more important to me than to have a parsimonious representation of the data. In this particular case you want to push for interpretability and say that I want a highly interpretable representation, whereas in this one I also want it to be very concise or compact. And more people are shifting to dictionary learning rather than sparse PCA, because at the end of the day the sparsity is there only for interpretability. It's not necessarily, once you put a constraint of sparsity you're not getting the optimal PCA anyway. So why bother with the orthogonality constraints and so on? Just directly go and apply this sparsity to a dictionary learning problem. Okay, next story. Now we are starting to move away a little bit slowly from PCA to other things. So what we have done so far, what I want you to think about is we started with PCA. This is still PCA applied to things. Then we went to kernel PCA. Then we said, okay, let's put sparsity constraints. Then we said, let's put dictionary learning. And now we are going further away. And we are saying that it's an alternative to PCA where the matrix components are required to be non-negative. It's useful for modeling non-negative data, images, text, trading volumes, etc. Here, I've been given a matrix, D by N matrix, X which is greater than equal to 0. All components of X are greater than equal to 0. Yes?
Even if in the negative data, if we normalize those values from 0 to 1,
yes?
Can we use the normalization?
No, you should not use it in that case. Because the thing is that when you have negative data, it basically means that there isn't a natural need for the matrix decomposition to be non-negative. So the reason that you were able to move it is that you probably moved it up using the minimum value so that it became non-negative, and then you renormalized it between 0 and 1. So that movement by the minimum is sort of artificial in some ways, and the minimum will depend on the sample that you got. So in the next sample that you get, the minimum might be very different from the minimum that you had. So from that perspective, when you work with data that takes both positive and negative values, artificially insisting that it's positive will cause problems. On the other hand, if your data takes positive and negative values, but you know by design you know what the minimum value is going to be and you shift by that, then perhaps you can use techniques like this.
So we know the extreme, so we can use the minimum value to do it.
Yes, but if you're doing a data-driven minimum value by standardizing the data, then this is not a good idea. But if you already know the range, then you can use that to shift things. Okay, so what we want to do is we want to find a matrix W and a matrix H such that W is greater than or equal to 0, H is greater than or equal to 0. And I want to get an X which is approximately WH. So here's a trick that people had suggested, which is to do the following. One approach to maximize this, one approach to get this approximation is to maximize this LWH. And what is this LWH? This is the log likelihood that you're going to get if you think of Xij, the ijth element of this is a Poisson distributed with mean value given by WHij. So you pretend as if these non-negative values are actually Poisson distributed values. Pretend. I mean, they need not be integers, but just pretend that if these were integers with the mean equal to WH, and you write out the log likelihood of that, you'll get exactly this expression. We did this in the morning. In the morning when we did the Poisson, it was x log lambda minus lambda. That was what the construction we had, which is exactly the same thing. So think about this to be the log likelihood that we are after. Okay? And now we are trying to maximize this both with W and H. And we're going to we'll detour into this minorization trick which will help us construct this function. So suppose, okay, we have good time. Suppose the optimization problem maximize x in x, fx is a hard optimization problem. Then you find another function gxy such that gxy is less than or equal to f of x for all xy, gxx is equal to f of x for all x, and max in x of gxy is easy for all y. Then this iterative algorithm, we saw this even yesterday, can compute a local maximum to the function. This is the same proof that I had showed you yesterday. This is the basis of the expectation maximization algorithm as well, this minorization trick. So how do I do this? So define, why do I have this S? Forget about these S's because I think I was showing to show some iterative thing. So don't think of, there is no S's over there. Define a number Aikj, which is Wik and which I know because W is greater than or equal to 0, H is greater than or equal to 0, this Aikj is greater than or equal to 0. Define Bij to be the sum of Aikj for k equals 1 through r. Now note that Aikj over Bij is a probability mass function because for different values of k, this is non-negative. I normalize it by the sum, so you end up getting a probability mass function. The concavity of the log function means something. So here's what we are going to do. I have the summation of k going from 1 through L, Wik Hkj. Why do I care about this? Because this is exactly WHij. The ijth element of the WH matrix is the summation of Wik Hkj. I multiply and divide by Aik divided by Bj, Bj divided by Aikj. This guy is a probability mass function. So I'll use my trick that I did with EM, pull that out. So instead of having a expectation inside, I pull the expectation outside. I get Aikj over Bij log Wik Hkj Bij over Aikj. Everything that's left over, I left it in there. Now I know that LWH is greater than or equal to this expression minus wkhjk. Call this function as a function of two variables, wh and wshs. How do I get? What is this wshs? Which is what I'm going to do is, okay, now I know why I call this h. So take the previous value of w and define this aikj using the previous value of w. There should have been an s here also. This is basically the same values computed from a previous values of w. So now this particular function has two components. It's got wh, which is the new component of w that I'm trying to compute, wshs, which is embedded in those a's that are there. And now I want to optimize this using, I want to optimize this over w and h. And it turns out that if you optimize this story, you will end up getting that the update equations come very nicely. Wik is the new value. If you look at the previous value of wh, the previous value of h's, multiply by them by w, you get the new value of w there. Similarly over here. And now basically using this EM type technique, you have an update equation of what's going to happen over here. In figure, which is going to come over here, they show non-negative matrix factorization, vector quantization, and PCA applied to 2500 images. Each image is a 19 by 19 pixel. So D is equal to 381. Positive values are represented by black and the negative values are represented by red. So the up here is non-negative matrix factorization. All of these are the PCA vectors that have been generated using the non-negative matrix factorization. This is the weights that are there on these, and you end up getting, this is the original, this is what ends up becoming the next one. This is vector quantization with the same story. You get whatever story you end up getting over here. This is what happens with PCA. When you do PCA, the images that you end up getting have lots of negative components. The combinations that you require also has lots of negative components to represent the same image. In general, this image reconstruction is going to be worse than that image reconstruction because you're putting more constraints on it. But on the other hand, the pictures that you end up getting here and the weights that you end up getting here has more interpretation. Non-negative matrix factorization, vector quantization, and principal component analysis apply to database of facial images. Details are given in the text, but unlike VQ and PCA, NMF represents faces by a set of basis images resembling parts of faces. So you end up getting these images are parts of faces because you're insisting that they are non-negative. And in some ways, that ends up becoming a nice way of doing things. Okay?
What is vector quantization?
Vector quantization is like k-means clustering. So you look at all the images that you have and you define k different means for them. And so not randomly, using a k-means idea, right? Because there is a k-means, a clustering technique. If I tell you k different means that you need, then it will generate for you k different centers for these images. And when you want to get a new image, you map it to the nearest center. So that's why you only have one non-zero component, because you map it to the nearest centroid. And then you get back, if I give you the original, the way to get back to this image is that you find the nearest k means and return that. And that's why the weight is only on one image. These guys are both decomposition type ideas. So this original image is decomposed into these weights on these images. Okay. So the one problem with non-negative matrix solutions is that they are not unique. If you have these are the values that you're trying to represent, any choice of basis vectors h1 and h2 in the open space between the coordinate axes gives the exact reconstruction of the data. Solutions to NNF problems depends on starting values. So it's not as if non-negative matrix factorizations are unique, so you have to be worried about it. And the reason for that is because they are non-convex. All right, I'll be right back. Give me one moment. Just need to get. I want to talk about yeah, okay, we'll do that later. 5 for 10. We could probably finish this. Let's see. Remember this PLSA idea that we had? Let me remind you what was LSA. LSA was this story here. You created this corpus of documents which has term frequencies TFJI multiplied by the inverse document frequency IDFI. This XJI is always greater than or equal to 0. By the way the things are constructed, so this matrix X is greater than or equal to 0. So now in LSA what we did was simply did a PCA on that. Now that we have the technique available of doing non-negative matrix factorization, maybe we can go and attack this problem with a non-negative matrix factorization idea. So PLSA is closely related to non-negative matrix factorization. Again, the matrix elements must be non-negative, but there is now a probabilistic interpretation of the matrix component. So suppose xij's are greater than or equal to 0 and the sum of the xij's is equal to 1. So x represents the joint distribution of a pair of discrete random variables u and v. I want to interpret x basically to be a way looking at the joint distribution of these. Suppose there exists a latent variable z that takes r values such that u and v are independent given z. So what's happening over here? Xij is the joint probability of u equals I and v equals j. Because I've renormalized everything, as long as x is greater than or equal to 0, all I have done is I've taken the sum of all of the x's and divided by the sum. So therefore the sum of the xij's now equals 1. So now I'm interpreting that xij is actually the joint probability distribution of u equals I and v equals j. Suppose there exists some random variable z which takes r different values. If I know the value of z, then x and y are conditionally independent. When z is equal to k, I have a probability distribution y is equal to j given z is equal to k. Okay, let me actually write this down and let me tell you what this actually means. Give me one moment. So let's say that xij is equal to the probability that u is equal to I and v is equal to j. Now suppose there is some random variable z that takes values 1 through r. Then I can always write this as the summation of what is the notation there, k taking values 1 through r, probability of u equals I, v equals j, z equals k. Right? You can always do this. This is a pretty simple idea that I just put that. Now I'm going to do the tower property, k equals 1 through r, probability z equals k, probability that v equals j given z equals k, probability u equals I given v equals j and z equals k. Again, I can always write this for any distribution. I'm just starting from this side. I take the unconditional distribution for z, conditional of v given z, conditional of u given v and z. We can always write that. And when we say that there exists a latent variable z that takes r values, that's simply that, such that u and v are conditionally independent given z, it means that I don't need this information. If I know the value of z, giving me the extra value of v is not going to be useful. Because u and v are independent given z. Then I can write the structure in this way. What happened? How did x show up here? U and v, x and y are the same things. So x equals u equals I, v equals j, and you're conditioning that on z equals k and z equals k. So call this matrix hkj, call this matrix wik, and now you have a non-negative matrix decomposition of them. Now we know that z is a latent variable, So you can use a modified minorization trick to compute local minima. You can basically design an EM type algorithm to be able to compute how to get this matrix factorization. Here's the story in gory detail. You choose RIZ, SJZ and PZ that maximizes this quantity. So RIZ is basically the distribution of I given Z, SJZ is basically this quantity, probability of V equals J given Z is equal to given Z, and PZ is the last part. I want to maximize this Xij log sum over Z, RIZ, SJZ, PZ. Multiply and divide by some arbitrary distribution Qj given Ij. Pull out what is going to happen, and now you have P, R, S and Q. You have one extra variable. Here you only have the variables P, R and S. Here you have P, R, S and Q. Let W denote the conditional distribution of Z implied by P, R and S. W turns out to be the conditional distribution of Z given I and J. This you can show that for that value, if you set Q equal to W, you exactly recover the same function back. So we are set for a minorization based algorithm. Repeat under set Qt is equal to Wt, Pt plus 1 is the argmax of this, that can be done easily. Rt plus 1 is the argmax of that can be done easily. St plus 1 is the argmax of that. You can basically show that Pt plus 1, Rt plus 1, St plus 1 have this structure, and you can keep going from there. So what have we done here? We started from here, and then we used our classic EM like trick. Remember in EM what did we do? We introduced this new distribution Q, which is exactly the same thing that I've done here. Pull the Q out, and now I have a lower bound that I can start optimizing. It's basically EM. Once you have the EM methodology, you can start applying EM to here, and that's what ends up getting the thing. And here's a picture that we got from PLSA. For document data in figure 15.8, this is the same data as this one. Where did it go? This one. The same document data that appears there. This is what happens when you did PCA on that, and this is what happens when you do PLSA on it. Here. So the Hinton diagram for the two basis vectors. Now the two basis vectors are very nicely defined. The two basis vectors you get here, three basis vectors you get over there. The proportionals of the three basis vectors, projections for the three basis vectors case is here. The solution is quite satisfactory since the first 1,000 documents are clearly considered to be from a similar ailments topic, right over here. The next 500 from other non-specific background topic. So these first 1,001 are coming from the ailment topic, then some background topic, and the last 500 are coming from a separate pet topic. Results of applying PLSA to our example term document matrix of K equals 3, where B is the W matrix, C is the H matrix. So B is the W matrix, H is the C matrix. And now you sort of see that very clearly what is happening here is that this is one topic, and then there is overlap of two subtopics over here. An advantage of this is now the interpretation can be made very easily because these topics are going to be non-negative, the weights are going to be non-negative. And in terms of computation, this is no harder than actually doing a PCA, because you just do an EM type method and you'll end up getting whatever you got from there. You can do conditional PLSA. Sometimes it's more natural to model Xij as a conditional distribution. Again, you can play the same trick, that there exists some latent variable such that things are in between. So V predicts Z and Z then predicts U. Conditional PLSA assume U is independent of V conditional on Z. Again, there are EM's time algorithms that can perform this PLSA, conditional PLSA. All right, we can stop here. We'll start again tomorrow on this.